In a Sandbox environment, an AI demonstration looks flawless. You give it a prompt, and it produces a perfect output. But deploy that same model into a multi-step enterprise workflow, like parsing an email thread with 10 forwarded headers, and that illusion of competence breaks. The model loses track of its overarching objective. This is Amnesia. It is the most expensive failure mode in production AI. Session continuity evaporates, and the human operator is forced to step in, repeatedly pasting context to reconstruct the state of the workflow. The standard reaction is to tweak the system prompt or purchase a larger context window. Neither solves the problem, because resets are the default state of real usage. Users switch tasks, tool outputs overflow the token budget, and conversation threads fork. The actual solution requires decoupling the compute layer from the memory stack. A large language model, or LLM, is a probabilistic text generator. It is extremely good at generating output inside a specific frame, but it cannot carry a timeline on its own. To survive session resets, you have to build persistent memory as deterministic infrastructure. This diagram illustrates the necessary architecture. An independent context API, an application programming interface used to retrieve state, sits outside the conversation, backed by a structured database. The LLM acts entirely as a stateless compute node. It queries the surrounding system architecture, which serves as the authoritative memory. The system is the memory, not the model. Once the memory is persistent, you have to protect what goes into it. In the enterprise, the primary source of incoming data is email. Email is an adversarial transport format. It is filled with invisible null bytes, inconsistent whitespace, and nested formatting. If you treat an email body like a clean document, a naive extraction pipeline will fail. Look at how this email layout expands. The model extracts a perfectly formatted phone number, but attaches it to the recruiter who forwarded the message, rather than the actual candidate. To stop this, the pipeline must treat the email like a crime scene. You do not ask the model to sort through the noise. You bag the evidence and isolate the relevant payload mechanically. This requires a hard, deterministic front end. It strips out control characters, normalizes carriage returns, enforces strict size limits, and detects exact boundaries of forwarded content. This entire gauntlet of pre-processing executes before a single token is spent calling the language model. By shaping the input deterministically, you restrict the number of identities the model can plausibly pick. This prevents the AI from confidently writing an incorrect identity into the system of record, saving downstream workflows from silent data corruption. With a clean input payload, the model finally runs the extraction. A widespread engineering assumption is that setting an LLM's temperature to 0, forcing the lowest variance output, creates the safest, most accurate data extraction. In reality, low variance decoding defaults to extreme caution when faced with imperfect inputs, like a partially obscured job title. The model omits the weak signal entirely to avoid making a mistake, resulting in silent data loss. Setting the temperature to 1 optimizes for high recall. The model acts like a stenographer taking best effort guesses at messy inputs. Operating at high recall introduces variance, so the architecture must compensate. You capture the messy strings, but force them through rigid code-level validators downstream. These validators are blunt constraints, entirely devoid of AI. If the model outputs a job title longer than 60 characters, or one containing a full sentence boundary, the code rejects it. This is the principle of asymmetric extraction. The AI proposes optimistically to capture every weak signal, but the deterministic code validates ruthlessly before any data enters the database. Extraction is only one source of truth. To build a complete profile, an enterprise system must aggregate facts from external data APIs, interfaces that pull in web scrapes, search results, and map coordinates. If you naively merge these incoming dictionaries in the order they arrive, the system will eventually overwrite a high-quality fact, like a scraped street address, with a low-quality AI guess derived from a phone area code. The solution is an enrichment cascade. Instead of tracking data sources at the overall record level, the system tracks provenance for every individual field. Each data source is assigned an explicit numeric priority to mathematically resolve conflicts. Lower priority sources are permitted to fill in blank fields, but they are structurally prohibited from overriding an established ground truth provided by a higher-tier source. Tracking field-level provenance forces the system to accumulate truth predictably. It eliminates the gamble of last right wins logic and prevents silent data degradation. Beneath the AI and data pipelines are the background workers, the processes responsible for claiming jobs, executing retries, and managing concurrent tasks. When multiple distributed workers attempt to process the exact same job simultaneously, you get duplicate emails, double database writes, and corrupted workflows. You fix this by modeling work as a state machine inside Postgres, a relational database, using the skip locked command. If another worker holds the lock, the database forces the next worker to skip that row entirely. This transforms a fragile, timeout-based coordination framework into a deterministic queue, where claiming a task grants an exclusive temporary lease. That same defensive posture applies to caching dependencies. In this architecture, the chosen cache is the absolute cheapest, lowest-tier instance available. Naive caches operate on a hidden contract. If the cache slows down, the entire application slows down. If the cache fails, the application errors out. You break that contract with a circuit breaker. If the cache fails, the breaker intercepts the error, returns a null value, and allows the main processing pipeline to proceed unhindered. True system reliability doesn't come from purchasing expensive, high-availability infrastructure. It comes from defensive architecture that degrades cleanly when dependencies fail. All of this underlying engineering serves one purpose: delivering processed, enriched, and queued data to a human operator through the final user interface. When an AI generates an answer, it produces raw, probabilistic reasoning. Streaming that internal chain of thought directly to the interface creates visual chaos, which is a severe liability during a live client presentation. The solution is dual-channel streaming. You separate the reasoning from the presentation. JSON events, a standard, lightweight data format, populate the final cards, keeping the raw text isolated. The final requirement for this workflow is searching the resulting data live on a shared screen without leaking sensitive client identities. The obvious impulse is to build a secondary, anonymized search index, but duplicating the index guarantees data drift and rankings that no longer match the primary system. Instead, you use a deployment pattern, privacy mode. It is a runtime toggle that redacts identity on the way out. The original search ranking remains perfectly static. Large language models raise the baseline capability of what enterprise software can parse and generate, but the surrounding architecture remains the absolute ceiling for reliability. The engineer's job is to build the deterministic memory, the field-level provenance rules, the transactional queues, and the strict code validators. That is the wrapper required to help a probabilistic model survive the crushing weight of enterprise reality.